So you have seen the video from Pre-Blue One Brown about the Fourier transform, and I guess you already have a pretty good idea of what it's doing, but let's see the math that surrounds it. Okay, so there's going to be some lecture notes, but it's not really lecture, it's just going to be a sheet with some formulas that will remind you of the properties that you have to be able to use. Okay. So, first, let's be clear about what's the difference between the Fourier series and the Fourier transform, apart from the formula, of course. So, the Fourier series, you remember that's for periodic functions or defined on a bounded interval. Okay, and for Fourier transform, so it's going to be for functions defined on R, or if you got that from the video, for something like a signal that is continuously coming in. Okay, so something that has, no specified length at first. So, the Fourier transform is going to be you take one function in and you have one function out. Okay, so the usual notations, some usual notations will be if you have your function f, its corresponding Fourier transform is usually denoted with a hat, and it's going to be a function of a variable. So in terms of variable choices, I will often use the French choice of variables for the Fourier transform, which is xi, the Greek letter xi. But then again, it really depends on the conventions that are used, and it's just a dummy variable. So usually, what is the formula we're going to get? So f of xi, it's the Fourier transform of f, is going to be the integral from negative infinity to plus infinity. So it's the integral on R of your function f of x e minus 2I pi x psi dx. Okay, so let me just underline where the psi appears, right? So what do we have? We really have a parameter-dependent integral. Meter-dependent integral. Okay, so that's one of the very important reasons why we studied that firsthand this year. Okay, so a bit about the continuity of this thing. What do we need? Let's see something that is very, very natural. So your exponential, of course, it does belong to L infinite. It's bounded above. If you try to, it at least it belongs to L infinite. Then what do we have? If you want to integrate that on, or it's not pretty clear if it's in L1, but however it's in L infinite, and if we are just asking for L to be in, for F to be in L1, okay, to be integrable, then that whole thing belongs to L1. And for instance, if you're wondering about the continuity of that whole function, then you can apply the dominated, not the theorem about continuity of parameter-dependent integral, and this inner function is going to be dominated by f, of course, so f of x exponential minus 2I pi x psi. So this is a complex exponential. So in terms of modulus, you get that the modulus of the product is the product of the modulus. That complex function has modulus, actually equal to 1. So that whole function is bounded above by f of x, which is integrable if f is in L1. Okay, so what does it mean? You apply your theorem on continuity of parameter-dependent integral, you get that this Fourier transform is continuous. Okay, so how can we denote that? We can say that the Fourier transform is going to be some transformation. Let's denote that some kind of calligraphic capital F that goes from L1 of R. Okay, you take an L1 function and you obtain a C0, well, at least C0 function. And well, it is a bit more than just continuous. Well, let's just write what we have. We take some function f in L1 and we apply the Fourier transform to f. So that's another notation, and you get some function usually denoted with a hat. It's going to be f hat. And so what are the main properties of this function? F hat is going to be uniformly bounded on R. Okay, and actually what we've already seen that. If you look at the infinite norm of the f hat, so I remind you, given by this above formula, if you are looking at the norm of that one, so well, if you take the absolute value of this function, so absolute value of this integral, it's going to be bounded above by the L1 norm of f. Okay, and so as f belongs to L1, this is going to be of class infinite, L infinite. Okay, so what else do we have? It's uniformly bounded on R, so another way to write that is that its infinite norm is bounded, okay? And we also have that it's decreasing to 0 at infinity, but this is something that is called decreasing to 0 at infinity. That's what is called the Riemann-Lebesgue theorem. And if we have time, we will show that in tutorial. Okay, or I will give you the correction for that, but that's an very important property. Well, important. That's says that f hat of psi goes to 0 as absolute value of psi goes to infinity. Okay, so it's a function that is more located more or less in a bounded area. Good. Okay, so let's take an example of the Fourier transform over some simple function. So let's do the Fourier transform of the following function, the indicator between some negative a to a of x. So for some a greater than 0, if you remember, that's we already called that function pi of x. That's because that's the shape of the function. That's the rectangular function. Rectangular function. Or another name that is often given to that, it's the gate function. Okay, because it just opens the gate between the on that interval negative a. So its corresponding Fourier transform is going to be given by f hat of psi integral between negative a and a, because I had the integral on R, and if I apply my indicator function, that's already reducing my interval of integration to negative a times my exponential of minus I 2I pi psi x dx. Okay, so then let's see what it gives us. So we know that we can integrate this exponential, so that's going to be minus 1 over so 2I pi xi. Okay, the integral is with respect to x, so the xi is acting as a constant. So that's if xi is different from 0, so we have to say if xi is different from 0, this is, sorry, psi is different from 0, this is what we're going to get, times the exponential of minus 2I pi psi x between negative a and a. So that's going to be, I get minus for the a, and that's going to give us a plus for the negative a. So we get e 2I pi psi a minus e minus 2I pi psi a over 2I pi psi. Okay. So what's this function? You might recognize the formula of the sinus function written with the complex exponential, e of theta minus e of minus theta divided by 2. That's 2I, sorry, that's going to be the sinus. So on here, that's just going to be the sinus of the corresponding angle. So 2 pi psi a, 2 pi psi a, and divided by pi psi. Okay, and that has a name. It's the sinc function, but we can just use it this way. So that was for psi different from 0, and if psi is equal to 0, f hat of 0 is just going to be given integral between negative a and a. So I've got the one function dx. So that's just going to be 2a. Right, so this is it. We've got the Fourier transform of my indicator function. Okay, that's given by those two formulas, 2a if psi is equal to 0, and that sine over pi psi for any psi. Okay, so we have also the inverse Fourier transform. Let's make it work. So the inverse Fourier transform that allows you to find again the original function once you have if you're given its Fourier transform. And if you remember, the idea is that if you apply the Fourier transform of the Fourier transform, that's going to give you the original function. It's something like this. Well, the formula is going to be f of x can be reconstructed by taking the integral so on or, and our variable is going to be the psi, so f hat of psi of e2I pi psi x d psi. Okay, what's the idea? If you remember the image in the video that was given of wrapping the function around a circle, trying to find the winding frequency of a function, this is going to unwrap your function because you're applying the exponential with an opposite sign to the one you had earlier. Okay, and notation for the inverse Fourier transform, usually it's f with a bar on the top. Why? Because obviously we are applying some kind of complex conjugate to the previous formula. Okay, so inverse Fourier transform, some usual notation, you can apply f to the minus 1 of f hat. You can also denote that as a conjugate of the transformation f, and that should give you the original function. Actually, you have the same kind of convergence. Well, this is an equality almost everywhere, and the equality is the same as for the Fourier series. It's everywhere for continuity points of f for x where f of x is continuous, and to the average, the mean value, at discontinuities. Okay, so if you remember from the videos, so the idea is that when you're doing the Fourier transform, you are analyzing the frequencies that a signal or a function has uh, in its data, in its information. And so the function you obtain, the f hat function, gives you the intensity for each frequency. Whereas when you're doing the contrary, you're rebuilding the original function out of the frequency. You can rebuild the intensity time signal that you had at first. Okay, so let's see some of the properties. We're going to do that in the next video.